In this lecture, we want to talk about Galois extension and Galois group. So say we are given a finite extension E over F, and we have degree of extension is equal to the order of the group, this automorphisms of field E which fix F. So there is an equality here. So if you have such an equality, then E over F is called a Galois extension, and E is called Galois over this field F. This group, automorphisms of E which fix field F, is called the Galois group of the Galois extension. So Galois extension is E over F. And we denote this group automorphisms of E over F as Galois E over F. So this is essentially just this group automorphisms of E which fix this field F. And you write this precisely if this condition holds, that the order of the group or the number of elements in this group is precisely the degree of extension here of E over F. Now if E over F is a splitting field for some separable polynomial, say f of x lying in this field F, so then the order of this group automorphisms of E over F, so automorphisms of E which fix F, is equal to the degree of extension of E over F. So this result, so this particular result, this we proved in the lecture on automorphisms of splitting fields. So in this lecture we proved this result. So this result looks exactly like this. So we want to use this to define the Galois group of a polynomial. So again start with this. So say f is a polynomial over field F. So f is a polynomial over field F, and this is a separable polynomial. So it's a separable polynomial. Then the Galois group of this polynomial f of x is this automorphisms of EF which fix F. So where EF is the splitting field for F. So this definition is motivated by this relation right here. So again you take a separable polynomial, find its splitting field which is E subscript F, and then you know automorphisms of E subscript F which fix field F are precisely the Galois group of this separable polynomial. So in the lecture on order of subgroup equals to degree of extension, we showed this. So G is a subgroup of automorphisms of E, and corresponding to G we have a fixed field E superscript G. So you denote E superscript G by F, then degree of extension is equal to the order of the subgroup here. So this was our lecture that order of a subgroup is equal to degree of extension. So we proved this result there in that lecture. So we want to use this result to characterize some Galois extensions. So instead of F, let us write here E superscript G. So now let this KH be a fixed field to some group H, and say this group H happens to be automorphisms of K which fix field F. So obviously this group H is a subgroup of automorphisms of K. So now we want to use this theorem here. Instead of E we have K, and instead of G we have H. So K over KH, so degree of extension, is equal to order of this group H. But this group H is nothing but automorphisms of K over F. So you write it like this. So this we are going to copy right here, and this we are going to copy right here. So H is equal to automorphisms of K over F, so obviously the orders are equal. So this equal to sign is coming right here, and this comes from the theorem here. So this theorem T is right here. Now we have copied this here. Now multiply both sides by this field KH over F, KH over F. Now this KH and this KH will cancel out. You have K over F on this side, and you have KH over F here. So this is extension. This is always greater or equal to 1. So if you skip this, then this greater or equal to will come here. So you have K over F, this degree of extension, is greater or equal to the size of our automorphism group. So the order of automorphism group which fixes F, and this automorphisms of K which fix F. Now there will be an equality only when you have an equality here. So this is equal to 1. So this is equal to 1 only when F is equal to KH. So let us rewrite this because this is important. So you have equality only when you have K over KH is equal to, so we have equality here. So this is only when F is equal to KH, but H is this group, automorphisms of K which fix F. So instead of F you are writing KH. So K over F is Galois if and only if F is equal to KH. So this is KH, so this is nothing but H here. So notice that this is H. So K over F, this finite extension is Galois if and only if this F is the fixed field corresponding to the group of automorphisms of K which fix F. So quite a mouthful, but this statement is pretty clear. So the second thing we want to prove is, so say you have an extension K over this field K of G. So this field K of G is nothing but fixed field corresponding to group G. So this field extension is Galois with Galois group G. So obviously this G is nothing but a subgroup of automorphisms of K. Only then you can get this K of G here. Now by definition this G fixes this field K of G. So that is the definition of K superscript G is the field which is fixed by this group G. So therefore G is a subgroup of automorphisms of K which fix this field K of G. So we do not know for sure that this is the entire group. We know for sure this is a subgroup because it's going to fix this field, but there could be something bigger than G also. So we don't know whether there is equality here or not. So we want to show that this is equal, and then everything else will follow. So this is a subgroup we know for sure. That just follows from the definition of K of G. So this implies that order of G is less than equal to order of this group. Automorphisms of K which fix K of G. Now since G is a subgroup of automorphisms of K, now instead of E you're writing K here. You copy this entire thing right here. So by theorem T, instead of E now you have K. So K over Kg is equal to order of group G, which is less than equal to, so this less than equal to is coming right here, and this is equal to K over Kg. So this, instead of H now you have G here. So this thing, say number 2 here, I'm copying number 2 here. So this you copy right here. So you get this. Now you see this is equal here, this is equal here. So this inequality therefore has to be an equality. So you have an equality here. And now you can see this Galois group is equal to this group of automorphisms over K which fix K of G. And this is the Galois condition also. So notice that this is precisely this condition here. Say we'll call this condition G. So this is also condition G. And that's it. So we have proven that K over K of G is Galois with their Galois group, which is Galois group is always automorphisms of K over K of G. But this group is precisely this group G with Galois group G. Now this above result 2 also shows that if there are two groups which are different, G is not equal to H, then their fixed fields will also be different. Now a big theorem which we will prove in the next lecture is this. Say you're given a field extension E over F. So this extension is Galois if and only if E is normal and separable. So in fact we will show that E is a splitting field. So E is a splitting field for some polynomial f over this f, and this polynomial f is also separable. So this we will show in the proof. So whenever we talk about normal and separable, we have to talk about some polynomial which is separable, and then the E is a splitting field of it.